Okay, welcome back to linear algebra. In this section 3.3, we're going to just take a look at how the theory we've been developing in chapter 2 and the first part of chapter 3 applies to the familiar kind of lower division linear algebra question of solving a system of linear equations. So I'm going to assume that you know what a system of linear equations is. You can stop the video here and just kind of look at this or look in your book where I took it from. It just establishes the notation. So we've got m equations and n unknowns. The coefficients and the unknowns all come from the scalar field f. And the parameters m is just the number of equations, n is the number of unknowns. And if you take those coefficients, the aij's, and just form this m by n matrix, we'll call that thing the coefficient matrix of the system. All right. So that's all very familiar. If you want to write this in sort of compact matrix equation, if we just denote by, say, x, this vector, a column vector x1 to xn, and then denote by b, another column vector in fn, b1 to bn, then that system S up there can be written compactly as a matrix equation. You just multiply the matrix A by the column vector X to get the column vector B. Okay, so this is also that same system, which I'm going to kind of try to consistently refer to as S throughout the entire lecture. Okay. So what do I mean by this? Here's some terminology. What do I mean by a solution to the system? Well, a solution by definition is an element of Fn that when you replace x with it, it makes the equation true. So a solution is a vector S in Fn such that AS is equal to B. The solution set, well, it's the set of all such solutions. Okay, we're going to call the system, remember capital S represents the system. The system's consistent if the solution set's not empty. So if you can find a solution to the system, it's consistent. Otherwise, it's called inconsistent. And some special terminology, if the vector B is identically 0, then the system is called homogeneous. Okay, so some language for our work. Here's the first result, theorem 3.8. If you take a homogeneous system, so notice that the author's writing AX equals 0. It's a homogeneous system. It's got m equations and n unknowns. And if we let K denote the set of all solutions to it, then K is nothing more than the null space of the linear operator L sub A, the linear operator on Fn, L sub A, or it's not an operator, sorry, it's a linear map. I do that all the time, a linear map, because it maps Fn to Fm. Okay, so that's one statement in this thing, that K is just that null space. Because it's a null space, it's a subspace, and its dimension is the number of unknowns minus the rank of that matrix, or the rank of that linear map, the same thing. Okay, the proof of this is really just semantics. We've done it all. By definition, you're a solution to that homogeneous system if and only if A times U is 0. That is, L of A of U is 0. You're in the null space. That's just the definition. Null spaces are subspaces. The final sentence follows from the dimension theorem, right? Because the dimension of the domain is n, and if you subtract the rank of the operator, you always get the dimension of its null space, right? So really, that's just sort of some rephrasing of theory that we've already done. One consequence of it is if m is less than n, so if the number of equations is less than the number of unknowns, then the system always has a solution. The system is always consistent. If the number of unknowns exceeds the number of equations, you can always solve the system. You can think of it as you have some sort of free variables in the language of lower division linear algebra. What's the proof of that? Well, we know that the rank of that matrix is never more than the number of its rows or columns. So because of that, then n minus the rank of that matrix would be greater than or equal to n minus m, which by our assumption is positive. Okay, but we just said above that n minus the rank of that matrix, that is the dimension of the null space. It's the dimension of K in the notation of the theorem above it. So if the dimension of K is positive, it can't be the empty set. If K is not empty, the system is consistent. Cool. So we're just kind of summarizing, enjoying all of our work from chapter 2 and the first part of chapter 3 here. Okay. This theorem is kind of parametrizing, in a sense, all solutions to a system if it has one. So let's just walk through the notation. So we're given another system of equations, AX equals B. Okay. And we're going to denote by K, capital K, the set of all solutions to it. And K sub H is the set of solutions to the so-called corresponding homogeneous system. Okay, so you just trade the vector B for the vector 0. Okay, so then what this theorem is saying is that the set of all solutions, K, to the system AX equals B is found by taking any one of those solutions, any S, and adding to it all of the solutions of the corresponding homogeneous system. So you take your S, you add K to it, you let K run over all the homogeneous solutions, and the theorem says you're going to get every solution to your system. I can't help but say to the abstract algebra veterans in this setting that the system, the homogeneous system solution, this subspace for us, it's a subgroup in particular. And this thing that we're forming is nothing more than one of the cosets of that subgroup. All right, so this theorem in abstract algebra language, I'm only talking to a few of you guys right now, but this theorem is saying that if you want to find all the solutions to a system of equations, you first find this subspace, the homogeneous solutions, and then you find any element that solves the system, and that element's coset will comprise the entire solution set of the system. There's a little tie into, if you're going to take the abstract algebra course next spring, when you learn about groups and cosets, you can kind of reflect back on this theorem, and that language will make sense to you too. Okay, the proof of this is just straightforward. The statement says two sets are equal, so I'm just going to do it by a pick-a-point proof. So I'm going to pick an element of the set on the left, this S plus KH, I'm calling it T. Switch my color here to draw your attention to it. So by definition, what does it mean to be in that set S plus KH? Well, it means you're S plus something in KH. All right. And then I claim that that's a solution. So what do? I just plug it into the equation. So I take A times T, substituting S plus K for T and using a little bit of matrix algebra. A times S is B because S is a solution to the system. A times K is 0 because K is a solution to the homogeneous system, and 0 plus B is B. All right. So T is the solution. So since T was an arbitrary element of S plus KH, that shows that S plus KH is a subset of K. So there's half our work. The second half is just reversing the implications. Now let's take an arbitrary element of K, take an arbitrary element of the set of solutions. And I want to show that it looks like an S plus some solution to the homogeneous. All right, so let's call it T. And then what do? I look at A applied to T minus S, a little bit of matrix algebra. A of T is B because T is a solution to the system. A of S is B because S is also a solution to the system, and B minus B is 0. All right, well, that shows that T minus S is a subset. If I call it, that's a lowercase k. T minus S, lowercase k, is an element of the K sub H, the homogeneous solution set by definition. All right, so just a little bit of algebra says that T is equal to S plus K, and that's exactly an element of this thing that I was calling a coset. All right, that's the opposite inclusion, so those two sets are equal. Nice. So that's one way to parameterize the solution set. Let's look at an example. In this example, I'm going to pull a couple of things out of thin air. The next section, 3.4, we'll talk about some computational methods to see these things. So I'm not going to try to show you how I found any work here. I just want to show you what that theorem 3.9 illustrates. So suppose that my system S is this thing. Okay, it's two equations and three unknowns. So I look at the coefficient matrix A. I've got it written there. And I can see that the rank of that matrix is 2. That's because I can see that it has two linearly independent columns. That's theorem 3.5. The number of linearly independent columns in a matrix is its rank. So that tells me by the dimension theorem that the null space, the null space of L sub A has dimension 3 minus 2 or 1. Okay, so the system is consistent. The homogeneous system is consistent because the null space is not 0-dimensional. So this is the part by thin air I meant. By inspection, you can stop the video and check that this element, little k, the vector minus 3, 1, 2, it's in the null space. It is a solution to the homogeneous system of equations. If you replace x1 with 3, x2 with 1 and x3 with 2, then both equations will equal 0. Okay, it's a one-dimensional null space. I've got a non-zero vector in it, so that non-zero vector is a basis for the null space. Capital N down there is N of LA. All right, so that tells me that I can describe the homogeneous solution space, N of LA. It's just the span of that single non-zero vector, so it's all the scalar multiples of it. So I take any t in my field F and I multiply it by that vector k, and that's exactly our homogeneous solutions in the notation of the theorem. That's our k sub h. So the theorem says if we could find any solution to the system S itself, we would add that solution to every one of these things in our k sub h, and we'll get the general solution set. So again, kind of out of a hat, you can check this, that the vector 3, 2, 2 is a solution to S. Where did I get that solution? Well, I'll tell you next time. But that vector 3, 2, 2 is a solution to S. I mean, you know where I got it too, but we're just going to talk about it next time. Okay, so then what does the theorem say? The theorem says if I take that S and I add to it every element of this set k sub h, so k sub h is described right here. I've got the element S, so you take those two red underlined vectors and add them together and you get this thing. There's one of them for every t. So theorem 3. I forgot already. Theorem 3. Sorry for the scrolling, 9 says that this set is the set of all solutions to that system of equations. Okay. Geometrically, if you want to think about this, I'm just going to throw it out there. That set's a line. That set is a line in the coordinate space F3. Cool. It's a line through the point 3, 2, 2 in the direction minus 3, 1, 2. A little bit of Calc 3 language there for you. Nice. Okay, continuing along here, a couple more sort of tributary results. The next one is about a square system. So if you have n linear equations and n unknowns, so it's a square system, ax equals b. The theorem says that if A is invertible, it's an invertible matrix, then that has exactly one solution. Namely, it tells us what it is, A inverse B. On the other flip side, on the conversely, if that system has exactly one solution, then A is invertible. All right, so if you want to write that in a single sentence, it's saying that for a square matrix A, the linear system AX equals B has exactly one solution if and only if A is invertible. Okay, so how does the proof go? Well, if A is invertible, if A inverse exists and we set S equal to that proposed solution, then you can just computationally check that it works. AS is A times A inverse B, that's B. So it's a solution. If S prime is some other one, I'm trying to show there's only one. If S prime is some other solution, well then AS prime is B. So multiply both sides of that equation by A inverse, and you find out that S prime is the same as S. So the solution is unique. Okay. On the flip side, if S is the only solution to the system AX equals B, well then our theorem 3.9 that we just proved says that the solution set is a singleton. The solution set is a singleton. But the only way this solution set, S plus the homogeneous solutions, contains only S is for the homogeneous solutions to be the zero space. Yeah, that homogeneous solutions is a null space. The null space is 0 means that the operator L sub A is 1 to 1. Remember, when a linear operator's null space is 0, it's 1 to 1. The dimensions of the domain and codomain are the same. So if it's 1 to 1, it's onto. So that shows that L sub A is invertible, but L sub A is invertible if and only if A is. So these proofs are going fast because of the machinery that we built in chapter 2. Okay. Last result that we'll talk about in this lecture, Theorem 3.11. It's telling us that when you have a system of equations like this, the system would be consistent if and only if, we're going to use this in our computational section next time, the rank of the matrix A and the rank of the augmented matrix A with the column vector B are the same. Okay, so it's kind of a way to check to see if there's going to be solutions. Check out the rank of those two matrices, and if those two ranks are not the same, then they're not going to be it's not going to be a consistent system. So I decided just to kind of bullet this out as a bunch of if and only if statements. So let's check it out. So the system is consistent, well, if and only if B would be in the range of L sub A, right? Because that system is consistent if it has a solution. So there must be some vector S that you can plug in here and it makes the system true. So that would mean that B was in the range of that linear operator L sub A, right? But the range of the linear operator L sub A, we've seen back in chapter 2, is the span of the columns of the matrix A itself. So here Cj just denotes the jth column. So B is in the range if and only if it's in that span, right? You can do kind of a pick a point proof here, but B belongs to the span of those C's if and only if the span of the C's is the same as the span of the set that you get by appending B to the C's. Here I've been a little bit lazy. I'm just trying to say if the dimension, if those two spans are the same, then the dimensions of those spans are the same. So I squeezed that in there, right? Two subspaces are the same if and only if they have the same dimension. All right, I should be careful about that. If those two subspaces are the same, they certainly have the same dimension. And then if the dimension of the span of C1 to Cn and the span of C1 to Cn plus B are the same, then those spans would have to be the same. So it's particular to these sets and how they're constructed. So should be a little bit careful about that. So what's written here is true. It's just, it's not true that two subspaces are equal if and only if they have the same dimension, but these are not just any two arbitrary subspaces. It's the span of a set of C's and then a span of the same C's plus this additional vector. Okay, we can talk about it in class. Those dimensions are the same. Well, the dimensions of those spans are the number of linearly independent columns. One would be the linearly independent columns of A. The other one is the number of linearly independent columns of the augmented matrix. But the number of linearly independent columns of a matrix is its rank by work in the first part of this chapter 3. Okay, so that proves theorem 3.11, and that's a little bit about how all of our theory kind of rolls together to tell us how solutions of linear systems behave. Certainly the main result, I'm going to scroll back to it, it's the number that I can't ever remember. The main result is this theorem 3.9, that if you take the solution space to the set of homogeneous equations, and you add to it any particular solution, that is in abstract diagonal language, you form this coset, then you will get the set of all solutions. All right, thanks for listening.